Everybody know what today's lecture topic is? What chapter we're covering?
Review.
We're covering a review, that's right. What does that mean about Tuesday?
Test.
Test. Everybody's thrilled. Test 2. Preview. Let's start with what she can have. Yes, basically, that's exactly what I expect. Basic for functions, scientific or engineering notation is, the kind of thing that will always give you blah, blah, blah times 10 to the 3n. Engineering mode is awesome. Get yourself a scientific calculator that has engineering mode. No graphing calculators. Scientific for function. 1 page. Double-sided cheat sheet. This is going to be filled mostly with tables, and I'll get to why it's going to be filled with tables in a second. You can bring the ASM sheet, which you should bring, because even though we've moved on to C, I may present you some questions that are written in assembly, and I would hate for you to get a question wrong just because you forgot what add I does. What does add I do? Add immediately. Most of them you take a good guess, but you can bring that. I will providing the register summary. I received an email about you. Just see me after class. I don't think it's a thing. You're not in trouble or anything. I will be providing the register summary. That's that sheet of paper that may or may not exist right around here that tells you where every bit in every register goes. Let's see if I can quickly pull one of those out. Yeah. Okay. That's okay. It is on the M drive. It's, register summary. You can print that out if you want to know what's there, but I will be providing it. It'll be stapled as the back page of your exam, so you can rip that off and use it as a reference. So bring the ASM sheet. I'll provide the register summary. You can have 1 page double-sided cheat sheets. And I said it's going to be filled mostly with tables because here's what's on the exam. Interrupts are on the exam. Now I've done a bit of annotation here on the right. These are the names, the C version names of all these interrupts. And the interrupts that we've talked about in sort of groupings, we've talked about external interrupts. That's on 2 very particular pins. We've talked about pin change interrupts. Those are on just about any pin. And each of these roughly deals with 7 or 8 individual pins. Then we've got the timer. These are all of the interrupts that can be fired by the timer. And really it's kind of split up across 3 different timers. Timer 0, timer 1, and timer 2. We have talked about our UART or our USART, which has receive, UDRE, and TX. You should know the difference between when the data register is empty and when we're done transmitting. We've also talked about the ADC interrupt. We dealt with that in lab. And I think that's where we sit. Other registers that you've used without really knowing it, you've definitely used the reset vector because that's just address 0. That's where we always start our programs. And there are a few that we haven't talked about that I will not be expecting you to know anything about. SPI, watchdog timer, EEPROM, analog comparator. Some of these we'll deal with after the second exam. So you should know how to at least set up these interrupts, how to turn them on. And there are 4 stages to dealing with interrupts, especially in C. 1, include. 2, peripheral. 3, global. 4, ISR. You've got to include the header file. You've got to enable the mask inside the peripheral. You've got to enable the global interrupt mask. And you have to provide an interrupt service vector, or interrupt service routine. So interrupts are on that. And this gives you a little bit of a hint of what else is going to be on it. All of these peripherals are going to be on it. So briefly going over all of these things. Here's your external interrupts. Int 0, int 1. You've got 2 bits of configuration for each of these external interrupts. And you can do things like low, any change, falling edge, or rising edge. You cannot do high level interrupts. Only low level. And they're the same. So you might want to throw this table into your cheat sheet because you will not have any other way to get it during the exam. Furthermore, there is always a mask register and a flag register. Why can't I send you to the back? Or there we go. A mask register and a flag register. The difference is mask is what tells what interrupts can, or what tells the processor what interrupts can fire. So if you put a 1 in the mask register, it means an interrupt can fire. The flag says, hey, an interrupt is fired. So I have 2 registers. So those combinations, control register A, mask register, and flag register, those are your external interrupt registers. Pin change, there's a bit more going on here. Okay, there's still a, no, don't move it. There's a control register and a flag register. Same setup. Control register enables. Flag register says, hello, something's happened. But there's even more masking going on here because each of these 7 pins, or 7 bits in each of these registers, 7 or 8 bits, corresponds to a particular physical pin on the device. And it's grouped up. So if you enable this guy, you further have to say which pins will activate. So you could set that pin high and that pin high, and then you would have 2 pins that would trigger the same interrupt. Okay. What do those pins look like? Well, they look like this. I have sort of highlighted what the groupings are, and they roughly correspond to ports B, C, and D. Okay, if you follow this around, port B is pin change in 0, 1, 2, 3, 4, 5, 6, and 7. Then port C is 8 through 14. And finally, port D is 16 through, where did it go? 16 through 23. There is no pin change interrupt 15. It doesn't exist. It would be right here, but it doesn't exist. Yes?
In the previous slide, when we had
this guy?
There was 4 bits.
These guys.
Yeah, so I'm a little confused about, so there are 2 interrupts, but in 1 register?
So the configuration is for both interrupts. So let's just go back to that list. I've got 2 interrupt sources here, int 0, int 1.
Right.
Okay, those correspond to particular bits. We can even look them up right here. Here, int 0.
ECE263.
Thank you. I'm just trying to find. Yeah, there it is. Highlight them. Correspond to those particular 2 bits or 2 pins. And these have special functionality. They can trigger an interrupt anytime there's a low level, or any edge, rising edge only, falling edge only. All of these things that say PC int, they're any edge. You don't have configuration ability there. You can mask off which ones provide you interrupts, but you cannot say how it provides you interrupts. You're limited to any edge, which is why in lab you had to do some kind of a test to know, because otherwise when you did like phase 2 or phase 1.5 or whatever, you'd press the button and it would increment, and then you'd release the button and it would increment again. So you had to do a test to add that piece in. So that's the difference. Okay. Okay, so that covers. Let's go. I'm going to keep going back to this because this is kind of my syllabus here. So I've got interrupts, external interrupts, and pin change interrupts. Then I've got timers. The easiest way to get up to date on timers is to head over to the data sheet, because each timer gives you a register description. Quite useful to have this. Okay. If you read this stuff up here, it goes into great detail. There's probably 10 to 20 pages worth of documentation on how this stuff works. But if you have a general idea, that general picture that we have, T count, an equality comparator, an OCR register, if you kind of remember that picture, flag, then you'll be okay generally with what's going on here. Again, I still see a mask and a flag. What's the difference between mask and flag registers? Well, it doesn't say anything. You have to read it, right? That was my favorite dad joke as a child. You'd say, get something. What does it say? Well, it doesn't say anything. You have to read it. Great dad joke. Yeah, mask is responsible for telling which interrupts are going to fire. Flag tells you which interrupts have actually fired. So then we've typically got some amount of control registers, and then here's my timer registers. I've got free running counter, 2 channels of compare. Timer 1. Let's look at timer 1. Mask register, flag register. What does the mask register do? Someone else? Tells which interrupt can fire, not which one does fire, which one can fire. What does the flag register do? Okay. Okay, so a few things that do change here. These are 16-bit registers. I talked, and you guys ran away while I was talking. I told you how to access 16-bit registers. I said it was very important how to access 16-bit registers, in what order. I told you that it was very important. You all tried to leave. So that will come back to haunt you. Friendly warning. And we've got some more control registers. We do have an input capture register, but I don't think I've mentioned it once, have I? Except in one context where it is the top value of CTC mode. We'll get to that in a second, but we're not going to talk about input capture or measuring pulse widths here. Oh, look, timer 2. We've got some control registers, our free running count and output compare, TI mask register. Somebody else, what's the mask register do? Dan. What's the mask register do? I don't care.
Tells which interrupt to fire. The flag one says
Hello.
hello.
All right, thank you. I appreciate that. We do have some interesting configuration registers. I'll let you look at those on your own time. Let's talk about what we can do to configure this stuff, okay? The configurations all follow the same basic patterns. What does that mask register do again? Oh, geez, nobody's answering. Nobody's answering, so I just assume that you guys haven't, it hasn't sunk in yet. The mask register tells which interrupts can fire. Oh, look, there's the mask register. So what interrupts are possible? This, by the way, if you see this is timer 1 because everything ends in a 1. Okay, so this is the timer 1 values. If you were using timer 0, it would vary ever so slightly. It would be a 0. So what are the registers that are possible? What does the TOIE stand for? Something you have to know, timer overflow. OC is output compare. So we've got 2 channels of output compare. Then let's break this down, all right? We have, let's not use that color because it's the same color as the background. We have WGM bits, and they, unfortunately, span two registers. WGM, waveform generation. We have clock source bits, CS bits. That tells us how fast the clock runs. We have COM bits. I should have done that in a different color. COM bits. That tells us what our output mode will be. So this is only for waveform generation. So we have normal mode, and toggle is really the only ones we've done. But we could do something where we clear and then we change the COM bits to set and then we change the COM bits again. Our clock select bits are very important because that directly affects all of our computations. So having tables like this is helpful. This particular table is for both COM1A and COM1B. It also happens to match COM0A, COM0B, COM2A, COM2B. It's all the same stuff. You need to look at these. Now this clock select bits here for timer 1 roughly matches timer 0 but doesn't match timer 2. What does timer 2 have that timer 1 doesn't, and vice versa, in terms of their clock sources? It's part of your pre-lab for this most recent lab. You saw it, at least in your pre-lab. No, they all have waveform generation because they all have COM bits. But some timers can have a finer resolution. Specifically, timer 2 can have a finer resolution because it's got a divide by 32 and a divide by 128, which you don't see here. So you might have to have two sets of tables for your clock source bits. Okay, this is the timer 1 list of waveform generation modes. We have only ever used normal mode and CTC mode. We have not dealt with PWM mode yet. So the things to really keep in mind are the top values. Okay. So again, ICR1, that's that 16-bit register that only happens in timer 1 for the 328P. You can use that as a top value if you also want to be doing waveform generation. This is the most flexible of modes for timer 1 because not only can you use output compare to cause PWM waveforms, but you can also use the top value. Or I should say this guy here is most flexible for PWM. But we haven't dealt with that yet. Don't worry about it. Normal and CTC mode on the exam. This is duplicate stuff for timer 1. Timer 0. Same set of COM bits. Mostly the same waveforms, but slightly reduced. So the waveforms that we have now are limited to normal mode, which always counts to FF, which you can use to make delays, or CTC mode, which you can also use to make delays, but you can also set it to be a recurring delay. All right, so things to keep in mind. You're going to have this kind of information here on your ASM, or not on your ASM sheet, on your register summary sheet. I'm going to include that with every exam. What you won't have is a table that tells you when you put a 000, that's normal mode. When you put a 010, that's CTC mode. So these kind of tables are important. You'll notice that the compare modes are exactly the same as timer 1, so you can consolidate there. All right, on to the UART. This one is the most mathy. Even though timers, we did tons of math, this is the one that people think is the most mathy. In terms of our registers, oddly enough, there's not a mask register here, which is odd. So chances are it's in one of these control registers. These are control and status registers. We are only going to be dealing with the USART in asynchronous mode for this exam, so you don't have to worry about synchronous mode. Let's go through, look at these registers, how this works. And for some reason, when I imported this from last year. It kind of got a little bit flubbed. Let's make it a little bigger there. So in the control and status registers, things that we need to know, we can turn on our devices, either receive or transmit, because remember this is full duplex. All of those vocab words that we talked about when I introduced the UART still apply. So we can set this up as a simplex receiver or a simplex transmitter. We can also set it up as a full duplex device. We have some control flags like the U2X bit. That changes how we calculate what our baud rate register should have. And we've got a flag here. Oh, I'm sorry. Oops, these are flags. These are all flags. These are the flags for the interrupts that can occur. Where is my receive enable? Here are my receive enable and transmit enable. Okay. So these are your flags. We also have some other flags here that we didn't talk about. Things like frame error, data overrun. But really all I care about is U2X and your flags. Okay. On our next control register, we can enable either the simplex receiver, simplex transmitter, or full duplex communication. We have our masks. Here are our masks. In the same spot. So our masks are in the same spot as our flags, which is helpful. We can use one bit pattern for both. And we can see a interrupt on receive of character when the data register is empty, and finally when both the transmitter is empty and the data register is empty. Okay, the rest of this is really all about setting up your frame specification. Your frame specification is usually set up as num bits, parity type, and stop bits. Usually some kind of a comma or something, and then baud. Baud stands for bits per second. A fairly common frame setup you'll see is 8N1 9600, which stands for 8 data bits, no parity, 1 stop bit, at 9600 bits per second. So to set that up, a couple of things have to happen. First, we have to turn on our device. We have to set our character size, and our character size is split up across 2 registers, right there. So we've got 3 bits that set up our character size. We have, where are we? Where's my parity bits? There they are. Parity mode, 2 bits for parity mode. We have a single bit for stop bits. Okay. Everything else should remain 0 for asynchronous mode. We do have a select mode, which is not going to be used for this. We don't use it. We only want to use asynchronous mode. As you're going through the register descriptions, you'll see more of these tables, but we only care about really these setups here. Baud rate, number of bits, parity type, and stop bits. We have not talked about how to set up your baud rate yet. Tables like this will keep you in good stead during the exam. Tells you what your size bits are, how you configure number of stop bits, and what your parity mode is. By the way, the 3 types of parity you can have are none, even, and odd. So if you see 7E2, which I did put on a previous exam at one point, that means 7 data bits, even parity, 2 stop bits. So what you would have to do is you'd have to set up UC, let's use a color that's legible, UCSZ. You'd want to set that to be 010. You'd want to set up USBS, 2 stop bits. You'd want to set that equal to 1. And finally, you'd want to set up UPM, parity mode, to be even parity, so that's a 10. Putting comments like this on your exam before you actually write your code gets you oodles of partial credit. Because even if you flub how you do it, I still know what you were trying to do, and I can say, all right, this was the correct thing. You knew what you were trying to do. You flubbed the execution a little bit, but you at least knew where you were going, okay? So putting comments like that, super helpful to me, and being helpful to me is helpful to you. Okay, baud rate register. It is a 16-bit register, so you do have to know how to operate on 16-bit registers. And there's two sets of calculations. One tells you what the baud rate is given a particular baud rate register value. The other tells you for a given baud rate or a desired baud rate what the register should contain. And the reason that there are 4 equations up here is one applies to the double rate mode, the U2X bit. All right. And all it means is you're going double fast, so you divide by 8 instead of by 16. There is going to be a certain amount of error in this. So one of the things I may ask you to do is calculate percentage error. Calculating percentage error is just like calculating percentage error for any other discipline. In the data sheet, I don't have it here, but in the data sheet, it does show you how you calculate percentage error. Okay, has something to do with desired baud rate and actual baud rate. Because when you run this through for a particular system clock frequency and a desired baud rate, you might get something that is fractional. And you have to choose whether you're going to truncate, you just get rid of all the fractional part, or round up. So you actually have x, x, z. You go up by 1. So you can choose to round up, round down, basically. And that's going to give you a certain error. So what you're going to do is you're going to take this xxz, plug it into this formula, and figure out what your actual baud rate is. So you might want 9600. We can do a quick one here. In fact, we did one in class. So let's say that I'm running at, 16 megahertz. So I do the calculation out, 16 megahertz divided by, parentheses, 16 times 9600 minus 1. All right, so what I get here is I get 103.166 repeating. So I have to choose, do I go with 103 or 104? Well, I'm only a little bit over 103. I round down to 103. So then I plug 103 back into this formula. 16 megahertz divided by 16 times 103 plus 1, close parenthesis, boom. And I get a baud rate of 9615.38, not 9600. Okay, calculating your percentage error then is a matter of comparing those two values. I'll leave that up to you to look up how to do that. But we did go over it in class. I could have also done it with the U2X bit on. I would have been dividing by 8 instead of by 16. So I could have tried it here. I might get a smaller error. So it's up to you to decide whether or not the U2X bit gives you a better result. Or I may tell you, you have to use the U2X bit, which means you need to know which formula to choose from. Okay. That was the whole exam in a big flurry of activity there. That's all the stuff that we're going to be covering. Oh, the ADC. The ADC is on this as well, isn't it? Let me quickly grab the data sheet. We'll do a quick review of the ADC. I'm sorry, I didn't have that prepared. Yes.
That slide with your drive.
Those slides are not on the M drive, but the video will be on YouTube. So let me just do a quick go over the analog to digital converter real fast. So the analog to digital converter, same register setups. We've got some control and status registers. So let's talk about the first one here. Actually, I'm going to do this here. I'm going to go duplicate. So now you can see that. I'm going to quickly go over here. Seems broken. So let's go to internal. Okay, good enough for me. So I'll write right on this here. When we're dealing with our ADC, a couple of things we need to set up. First, our reference. Second, our source. Okay, our reference tells us what our maximum value can be. So in our case, we chose for lab that we wanted AVCC to be our source. That's 5 volts. Okay, this is the table associated with those reference bits. So I can tell you use whatever reference I want. Okay, the source bits tell us what we're using. So we can measure a couple of things here. We can measure from our 8 inputs. We can measure our reference voltage, our band gap reference, or we can measure ground. Measuring ground is an interesting thing to measure, right? What should ground always be? 0. But if it's not, something is a little strange. It says here ADC8. What it really means is the temperature sensor. Okay, I was able to divine that because there was a 1 next to it. So I just read that. But there is a temperature sensor on board, something we can look at. In terms of control, the third thing we need to set is the prescaler. Prescaler requires a little math. You definitely want to pick up a little scientific calculator for this. The math is pretty simple. We have these prescalers. These are the possible prescalers. We've got 2 twice, 4, 8, 16, 32, 64, 128. And we need to take our system clock and get it down to less than 200K. Why? Because accuracy. That's why. Okay, if we go faster than that, the last couple of bits won't actually reflect the values. Okay, so we have a, how wide is this ADC, by the way? How many bits of resolution? One of those vocab words. 8 or 10. Can it be both? Well, good question. Let's go back. One bit I didn't circle up here. What does ADLAR stand for? It's impressive, especially because it's up on the screen. Yeah, right there. I figured if I suddenly was like, oh, geez, you would see it. But yeah, it's the left adjust. So this does do 10-bit measurement, but we can treat it as an 8-bit value by ignoring those least significant bits. It all depends on how it shows up in the ADC register. Okay, so for our control, we do need to set up our prescaler. All we have to do, if we want to know what our divider has to be, is take our system clock. So let's say our system clock is 12 megahertz, number I picked out of the air. Divide it by 200K, e to the 3. So I get 60. I need a clock divider that is at least 60. So what clock dividers do I have available to me? Well, I've got 64. 64 is greater than, okay, so I can use that. 32 is less than, so I cannot use that. That's all you need to do. It's a single division. Okay. Back to the conversion. We do have the thing that says start a conversion and enable. We also, in the same register, have both our mask and our flag. What's the difference between a mask and a flag? Well done. I'm proud of you for humoring me. And The auto trigger enable. If we want to do things without any CPU overhead in terms of not doing things, we can use the auto trigger enable. And once we start it once, something else will trigger it from then on. The most useful one is free running mode. That'll always be transmitting. Yes?
For free running mode, is it always going to be recording into the ADC?
Yeah, so you can miss samples if you don't grab them immediately. So it's best to use an interrupt and then throw it in some kind of a buffer. So what things can trigger the auto enable? Well, there are the auto trigger source selection bits. Free running mode, counters, external interrupts. External interrupts are useful. This, by the way, is not a pin change interrupt. This is external interrupt 0, not pin change interrupt 0. That's really all that's here, the auto trigger source bits. The last is the actual ADC register, and you can see here that there's two ways it can be used. Either you look at it in full 10-bit mode, okay, which is left adjust being 0, or you can grab just the high byte, and that's 8-bit mode. Yeah.
So if we had a button set up to interrupt 0 or 1, that means that we could have had it not use a button interrupt and then check the thing. We could have had it set up to rising or falling specifically.
Yeah, unfortunately that dev board does not hook up the onboard button to D2 or D3. So you had to use a pin change interrupt to do that. You could have hooked up an external button, another button, and then pressing that button, you could have chosen rising edge or falling edge, and then it would have automatically triggered. I do want to give you a word of warning. Sorry, just got to get Hamilton out of my head for a second here. Give you a word of warning. If you use free running mode, you can't just turn on free running mode and it goes off. You have to start it once, okay? Once you press play effectively, then it will continue on. But if you just set everything up for auto trigger free running mode, it doesn't start converting, okay? Even if it's enabled, you have to start the conversion once, all right? And then it will continue to fire interrupts. Only if you've set the, what flag, which thing, which bit, which byte? Yeah, the interrupt enable bit. Okay, so that actually that's one more piece that's going to be on the exam is the ADC. So for the rest of this class, I will answer any question. I will write any code within the bounds of good taste that you want to talk about. We can talk about any peripheral. We can do any kind of calculations. It's up to you.
Can we take like these tables right off something, paste them and print out, or?
So you get a page double-sided. I would suggest, if it were me, that you build up like a little Excel sheet, because the tables that come out of the data sheet are stupid big and wasteful. Like, look at all that wasted space. You don't need that much wasted space. You don't even need this title. You know what's going on, right? Division factor. Okay, we get it. So shrink this down, okay? You don't even need to list out all 3 bits. You can 0 through 7 is really all you need. So, build it yourself. You can fit a lot more nicely. You can make it good. But yes, the answer is yes. If you wanted to do that, you could. I wouldn't.
Just make sure it didn't have to be handwritten.
No. No magnifying glasses, like standard. Don't be ridiculous. All right. If you fit so much crap on this piece of paper that you need a magnifying glass, you have not studied enough. All right. You're screwed going in. Sorry. Truth hurts. But absolutely, computer, why would you ever? So once in middle school, I was disciplined, and I had to write, "I am very sorry," or something like that, 100 times. So I opened up like Word 1980 or whatever it was, and in a cursive font, I wrote, I actually typed it out. I didn't copy and paste, but I did type it out 50 or 100 times, whatever. She was so mad. And, well, anyway, that was the story. What else can we do? Yes?
Maybe a timer calculation?
Sure. Let's do something about waveform generation. Because waveform generation has got a little gotcha that, oh, no, everything is wrong now. As you may have seen when we started, let's just make sure that this is in fact, there we go. Still going. New page. So let's say that I wanted you to generate the following. A square wave with a period of, I don't know, let's say 50 microseconds. 50 microseconds. Okay. The first gotcha in this kind of a problem is that 50 microseconds has nothing to do with this problem. The thing that has something to do with this problem is 25 microseconds. Because we're doing waveform generation, so an event happens twice a cycle. It happens here, and it happens here. There's my cycle there. Okay, it happens twice a cycle. So we've got to do some math. In order to solve this problem, you need to know what your system clock frequency is. So let's assume that we're running at a system clock of 1.2 megahertz. That's my system clock frequency. Okay, well, we can attack this problem in a couple of different ways. We can do it all algebraically, then solve once, but let's just find some numbers here. So if our system clock frequency is 1.2 megahertz, that means the period of our system clock is 1 over that, right? 1 divided by 1.2. Can't write things. 1.2 megahertz. Or 833.3 nanoseconds. So in this case, it's going to be kind of tough to draw this forward all the way because this is an irrational number. So if we just grab this, it's not going to work so well. So I'm going to have to always be referring to 1 over 1.2 megahertz. But let's now take that so we can figure out how many system ticks in 25 megahertz, 25 microseconds. So 25 microseconds divided by the period of the system clock is equal to the number of system ticks. Okay? And unfortunately, we can't use T-system because it's irrational and I can't type in an infinite number of 3's after the decimal point. But we do know that that's just 1 over the system clock. So what does that mean if we rearrange this a little bit? 25 microseconds times 1.2 megahertz. Seconds cancel with hertz. Okay, and we're left with micro versus mega. Mega is 10 to the 6, micro, okay. So we're left with 25 times 1.2. And if I had cleared that, 1.2 times 25, 30 ticks. So all that means now is we need to set up our system for CTC mode. The OCR register needs to be set to 30 minus 1. Another gotcha. 30 minus 1 because it happens when it goes from the maximum value to 0 because 0 counts as a thing. So it's always minus 1. It's every 30 ticks, which means 0 to 29. Yes?
What's that called when 0 is the starting point and 1 is the starting point?
Indexed. You would say something is 0 indexed or 1 indexed. That's the first thing that comes to mind when you ask me that question. Or based, 0 based array, 1 based. And we've got to set up our waveform generation mode. Oh, that is our waveform generation. We got to set up our COM bits though to toggle. Now, this is the first set of things. I now need to go look up in a table what CTC mode is and which CTC mode I use. That depends on which timer I'm using. Okay, if I'm using timer 1, it's a 4-bit WGM bits. If I'm using timer 0, it's 3 bits. You notice I didn't put a number here. I didn't say OCR 0 or OCR 2. And I didn't put, COM 01 or 11 or anything like that. Toggle. So I've got to look that up. I need to know that toggle, well, I can go back, right? Pretty sure it's 01, but let's not jump to any conclusions here. Toggle is 01. So now I know that this is going to be 01. CTC mode is, anybody off the top of your head know what CTC mode is? 010 is what I came up with too, so that's good enough for now. Okay, and 30 minus 1 is 29, so I'm pretty sure I'm good there. So that's a good example of what's going on, and I kind of attacked it in a couple of different ways. Okay, with 16 megahertz, it's a little bit nicer because I get a nice rational number. 62.5 nanoseconds is the period. So I can go at this, and in the end of the day, I noticed that everything canceled. My final calculation was 25 times 1.2, okay, because megahertz canceled with microseconds and so forth. What didn't I have to do in this problem? Normally, it's a little bit more complicated. What bits didn't I set? The prescaler. So it is wrong to finish this problem without the prescaler, okay? But CS, I know that I want to be divide by 1. Okay. It just so happens that the amount of time I want to delay in conjunction with my system clock means I don't need to use a prescaler. But if I upped this to say milliseconds, let's look at that. If I change this to milliseconds, what would happen? Well, now I'd have to do the same thing, right? 25 e to the -3 times 1.2 megahertz e to the 6th. And now I end up with 30,000 ticks. Okay, so now there's a couple of ways of going at this. Okay, I know I need to use a prescaler because what's the magic number? If it's over a certain magic number, I know I must use the prescaler. Yeah, 256. If it's 256 or greater, I need to do something. So I can look at this a couple of different ways. The prescaler is going to affect things. So first off, I could look at the number of ticks and divide the number of ticks. So I've got divide by 1, divide by 8, divide by 64, divide by 256, divide by 1024. Okay. Well, divide by 1 is just 30K. Divide by 8, this is a nice rational number, 30K. Divided by 8 gives me 3,750. 30,000 divided by 64 gives me 46.875, which is going to give me some inaccuracy, okay? Going to give me some inaccuracy. 30,000, did I do 3,000 before divided by 64? I did. Need to move that decimal point over just a tad. I didn't put the correct number of zeros in. So that's 468. So this is still not valid. Okay. Keep in mind while you're doing this what your answers kind of should be. I just, 64 versus 8, it's like a factor of 8. So I shouldn't have gone down to less than 100 from 3,000. Okay, 30,000 divided by 256. This one maybe 117.1875. So this is the first one that is less than 256. We will see a little bit of inaccuracy here. Okay, we could calculate our error by basically reversing this process. Okay, I'm not giving you any hard and fast formulas here, although they exist, okay? When you go onto an online calculator, it just has a couple of formulas that it pops in there and tells you what's going on. But knowing what's happening here, so this was one way to attack it, was to divide the number of ticks. The other way to attack this problem would have been to adjust your system clock frequency. So 1.2 megahertz, all right, why are you not working? Divided by 1. Okay, 1 divided by 1.2 megahertz, that gives us our system clock period. But if we have a divider, we're effectively just going to be multiplying that. So if I multiply the system clock frequency by 8, I end up with 6.67 microseconds. If I multiplied it by 64, I get 53.33 microseconds. And then I could take that original number, 25 microseconds, and divide it in. Okay? I feel like I've made a small mistake somewhere, but I'm not quite sure where it is. Yes?
So how would that change the code again?
The code would end up the same. This is two ways to attack the same mathematical problem. Okay? You're just trying to figure out this number right there.
Right.
Okay? So if I had tried to do this with milliseconds, okay, I could have said, all right, I need 30,000 system ticks. A system tick is 833.3 repeating nanoseconds. Okay, so to get to 50 milliseconds, I need 30,000 of those ticks. So then I said, all right, well, if we divide that number of ticks by our clock divider, we get these numbers of ticks. And those are pre-scaled ticks. Okay, so 117.18 pre-scaled ticks. All right. The other way of looking at this is instead of finding out how many ticks you need, figure out what your pre-scaled period would be. Okay, because remember, what we're effectively saying is between this point and this point, 30,000 system clock periods are going to happen. So if I did a system clock divided by 256, that means 256 pre-scaled clocks are going to happen. So you can look at it either way.
But the OCRA, that still remains 30 minus 1. And then
the 30 minus 1 is for microseconds. I redid the calculation for milliseconds. So instead of 50 microseconds, 50 milliseconds. And that's where you'd come up with this 117 number.
And you would sign it to OCRA?
Correct.
Okay.
Okay, but you'd also have to change your CS. So you could say 117, and here you'd have to be divided by 256. Other than that, it would all stay the same. Okay? How was that for a timer problem?
That was good.
Thank you. Was there more that you, like something else you wanted to hit on the timer?
I think that's it.
All right, so this is for waveform generation. So there's that first divide by 2 that you have to address. Okay, if you gave me this for, in fact, I think I did it wrong here. No, I didn't. I'm all set. All right, 25 microseconds. So I did 25 milliseconds for my calculations. So if I was just asking you to do a delay, you wouldn't have to do that divide by 2 shenanigans. Other than that, I mean, you're really just setting up the registers. And the registers we've talked about, I think, pretty well at this point. Here are the registers for timer 1. You've got comm bits, waveform generation mode, clock, source. Everything else is interrupt related. Okay. For timer 0, same stuff. Comm bits, waveform generation mode bits, clock source bits. Just choose what needs to go in each of them. Don't leave any of them blank. Don't leave an input blank. All right? And please do, where am I? Please do put comments like this. Let me know where you're trying to go. Okay? So you don't have to immediately just say WGM is going to equal 0, 1, 0. Say you want WGM to be CTC mode, and then put a number next to CTC mode. say that you want your comm bits to toggle and then tell me what that is. Because if you copy this wrong without giving me this, then I think you just don't know what you're talking about. Okay? If you put a divide by 1 here, but you put the wrong bits in, I can still give you partial credit for saying, all right, I want to divide by 1, or I want to divide by 256. All right? Other questions?
Does a normal function in C and interrupt service routine run about the same time, speed, if they're the same number of clock cycles?
Does a function and an interrupt service routine run in the same time if the instructions are the same number of cycles?
Does it take more time to get into a function, or the service routine is the same?
And how accurate do you want this answer to be? Within a clock cycle or two, I think you're okay. I would have to look up the return I instruction just to make. Oh, I found it. This is what I'm going to give you on the exam. I showed this as all of the registers that are relevant to us, including whether or not they're in I/O space or in general memory space. But what I was going to look for here was not that. I was going to look for an ASM sheet. So what I would have to do to confirm that answer is, first off, is return I the same timing as return? And I think the answer is it is. The only sort of offset you might see is because of the calling overhead, right? You have to call that function, so you need a call instruction. Whereas an interrupt doesn't get a call instruction, but it does change out all the program counter stuff. My guess is at the end of the day, it might be 1 cycle slower one way or the other. The answer to that question is contained within the data sheet. You just have to read a little bit more on how interrupt service routines are handled at the processor level. Okay? I don't have that information rolling around in here right now.
All right, that's fine.
Other questions?
When you're figuring out the prescaler, I know you stop once you hit one that was within the limits of it.
Yep.
Would it be wise to go to the next one and see if maybe that would
It's
fit better and have less error?
You could. I sort of looked at 1024, and 1024 doesn't go evenly into 30,000, but let's do it. Let's find out what it does. 30,000 divided by 1024 gives you 29.3. And the thing to know about this is that 0.3, first off, it's farther away from an integer value. So you're going to have more error. But it's even worse than that, because that's 0.3 of 1024 ticks. This is 0.18 of 256 ticks. So it's even worse error than you might imagine. Okay, but it is good to look. If it had happened to work out exactly, that would have been a thing. However, since 1024, one of its factors is 256, you know that you're never going to get better.
Yeah.
Right? So if it went into 256, or if it went into 1024 evenly, it would also have gone into 256 evenly. Because powers of 2. Okay? Other questions? Yeah.
You said something earlier about when we're correcting our, calculating our error,
Yeah.
percentage error.
Sure.
What do we use that for again?
Figure out how off you are. It's percentage error is in anything that you would measure. So let's just quickly go over here to the UART calculation of. There it is. So at the top of the page, let's zoom out a little bit. At the top of this page that shows all of your tables. By the way, I will not be giving you a processor frequency or a desired baud rate off of this table. Don't throw this table onto your thing. Okay, learn the formulas. It takes up a lot less space. So here's how you calculate your percentage error. It's the closest baud rate that you can get to match over the desired baud rate minus 1 times 100%. So the closest match that I'm talking about here is, let's go back to that calculation we did just a little while ago. Oh, here it is. So if the closest that you can get is 9615, okay, this is your desired baud rate. So actually calculating this out, you're just going to take the closest match divided by the baud rate minus 1 times 100. Let's do it out. 9615 divided by 9600 minus 1 times 100%. Here we go. 9615 divided by 9600 minus 1. Oh, times 100. That's why I'm getting weird numbers. 9. 15% doesn't seem right. 15% error is not what I expected. Let's just quickly check that on the data sheet. Oh, what did I use for... What did I use for an oscillator frequency? No, I used 16 megahertz. So I can actually check that out. No, come on. The problem is every single thing right now looks like it's from the data sheet. Oh, it's also up on this screen. That's why I can't see it. So if I go down here to 16 megahertz, there's 16 megahertz, 9600. Yeah, 0.2 sounds a lot better. I'm not sure what I did wrong in that calculation. Let's try that one more time.
I get the calculations.
What did I do? I guess they rounded it up. So that's 0.156%. 0.156%, they rounded up to 0.2%. So the table isn't even right. It's close enough. I mean, 0.2% error. And if you were to try to do, we can try to do one more of these here. So things like this have a much higher error percentage. And then when we use numbers that are power of 2, we get a 0% error because they're exactly the same. Yes?
I end up with a negative % error.
Well, think about it in terms of what our actual equation is. If I could get to the right. Okay, you've got this over this minus 1. So how would you make this quantity negative?
Less than 1.
Yeah, so if it was less than 1. So if this number, 915, was smaller, right? You subtract that from 1. This is going to be a ratio, right? So right now this is a ratio that's higher than 1. If the numerator was lower than the denominator, you'd end up with a negative number. So it implies that here we're running fast, right? If we rounded a different way, we'd be running slow. And so that plus and minus means either your clock is running fast or running slow. That's how the negative applies. Okay? In terms of our absolute error, doesn't matter, but it might for some instances. So the percent error is tells us both speed and distance from our desired. Other questions? I think perhaps ADC resolution might be something you want to go over. Let's think about that for a second. Because for a given VREF, okay, especially if we have differential, but your VREF would be something like 5 volts. Your VREF negative would be something like 0 volts. You could have something that is a differential measurement, okay, or You could have a different negative reference. Most things are ground referenced. If I wanted to know my step size, because that's one of those things we need, step is 2 to the resolution. So resolution would be something like 8 bits or 10 bits. Yep.
Is the ADC value signed?
No, because it is referenced to ground. In the ATmega32, we can actually get signed numbers because we can do differential measurements, but not in the 328p. So if I were to do this, I could take my voltage, 5 volts minus 0 volts, divide it by 2 to the 8, and what would I get? Well, that's just 5 divided by 256, 19.53. What are the units on this answer? Well, I've got volts on top and steps on the bottom. So I would say that that's 19.53 volts per step. Volts per step. So every step means that you've gone an additional 19.53 volts. Let's do another calculation. 5 volts minus 0 volts over 10 bits. What is 2 to the 10? 1024. And that gives me a number that's roughly 4.88 millivolts per step. I should have said millivolts up here as well, not 19 volts, 19 millivolts. Yeah, no. So you can't measure higher than 5 volts. 19 volts would not make sense. So it's millivolts per step. So then another question I could ask once you've kind of calculated these values, if I have 3.3 volts in, what do I get for my digital output? I know I didn't spell digital correctly. Digital. How would I figure this out? What would my digital output be if I have a particular analog voltage? Well, it's as simple as in divided by step size. My input is 3.3 volts. My step size is 4.88 millivolts per step. So calculate that out. That's 3.3 divided by 4.88 millivolts. Darn it. Millivolts per step. That gives me 676.23 steps. And that is the first trap. This is not the answer. It's either going to be 676 or 677. It's an integer value. Has to be. All right. Now, let's redo one more here. I want to do 3.33 volts. Let's calculate that out. 3.33 divided by 4.88 millivolts. Oh, I went up, excuse me. Yeah, 3.303 volts. Oops. I just wanted to illustrate a point here. 3.3 6.303 volts gives me 676.84 steps, which is also going to truncate down to 676. So two different voltages give me the same answer. Okay? So that is going to be an amount of error in your calculations. Okay? It only has a certain resolution, and that's what it's talking about. It can't tell the difference between 3.03 volts and 3.3 volts. As far as it's concerned, it's the same number. In fact, let's calculate out what does it think 676 steps is in voltage. How would we solve that? New page. 676 to a voltage. All right, well, we know our step size is 4.88 millivolts. So all I'm going to do is I'm going to take 676, multiply it by 4.88 millivolts. And I get 3.3 volts. Now, I'm going to take 677 for funs and giggles here. 677, multiply it by 4.88 volts. That's not right. I'm somehow got into fixed mode. How do I get out of fixed mode? There we go. Floating point mode. Ah, there we go. Let's try that again. I was about to say, that didn't sound right. Okay. Excuse me. Equals 3.29888. Then do 677. 3.30376. Okay, so these two numbers, any voltage between those two numbers, as far as the processor is concerned, is 676. If you are less than this number, 3.30376, greater than or equal to 3.29888, the number you're going to get out is 676. That's your resolution and any error in there. So if you have a signal that's twiddling at less than 4.8 millivolts, you're not going to see the difference. Okay? Other questions? We're about out of time, but we can do one more quick one if you like. Okay. Basic differences between pin change and external. First off, if you think of your processor, it's got port B, C, and D. Pin change interrupts can happen on just about any port that you want. And this is kind of roughly where those ports live. Okay, so they can happen on any of them. Pin change, any pin, and it's always both edges, I should say, both edge. It's non-configurable. 3 interrupt vectors for all 23-ish pins. So they're grouped together. Contrast that to external. Only happens on 2 pins, and I think they're about there. Okay, D2 and D3. They can be level, triggered, low level, any edge, or rising or falling. You can choose. Furthermore, these work in sleep modes, but you don't really sleep. That may come in handy to you, semesters down the road, but external interrupts can wake this out of a deep sleep mode with level sensitive, I think. So they're a little asynchronous. They don't necessarily rely on the system clock, whereas pin change interrupts do. The system clock has to be running for that to work. But the main difference is each pin gets its own wake. Each pin has its own interrupt vector. Okay. Those are the big differences. Okay, so pin changes can happen on anything, but you must deal with a trigger on rising and on falling. Whereas external interrupts only happen on two particular pins. There's an interrupt for each pin, and you can choose how they fire. Okay, takes a little bit of extra configuration with the interrupt sense control bits, ISC bits. I think interrupt sense control bits. That sounds about right. Interrupt sense control bits, yeah. So you can choose which size you want or which kind you want, low level, any change, falling or rising. Okay, and you can do that independently for both external interrupts. And then they each get their own interrupt vector. Whereas pin change interrupts, any pin change interrupt on this port basically happens all at once. Okay, so it gets kind of interesting when you have three pins that are all going to cause pin change interrupts. They're all triggering the same interrupt service routine. Then you have to figure out which one triggered it. Okay, so you have to know what their previous state was, and then you check their current state. You have to check for rising and falling. There's a little bit more to it. If you just want a single one, it's not that big a deal, but those are the differences. All right, so Tuesday, I'm going to assign seating, split you up, all that kind of stuff. I am going to attempt, I don't promise this, but now that we're on Office 365 stuff, I might be able to actually do mail merged emails. So I'm going to try and send you your seat beforehand via email. Do not respond to that email because I will be sending it out to everybody as a separate thing. If it doesn't happen, it'll be up like it always has been, but it'll be a good test. Close that down.